3x squared plus 4. That's the differential equations, correct? Why? Because it involves a derivative. We could have y prime equals 2x plus y, right? And then normally we'd substitute something in for y because we'd have the y prime in terms of x only. But every once in a while they might just give this to us and say, hey, find a solution to this, or does this function satisfy this derivative equation or differential equation? They might say y double prime minus y prime equals 7. And they'll say, does y equals blah, blah, blah satisfy this differential equation? Okay. What else could we have? We could have this is second derivative equaling some stuff. We could have x's and y's on both sides. We could have a number of things. Okay. So it's going to look a little weird for us every once in a while because we're so used to this nice, neat derivative equation. But in reality, this stuff isn't too bad. All right, verifying solutions to differential equations. Determine whether the given function is a solution of the differential equation y double prime minus y equals 0. Okay, what's your first thought? Because sometimes we see something kind of weird. We have to think about what do you think we should do and then probably do it. So in this situation, what do you think we should do? And then what? You're onto something. I know what you mean, but say it better. Yep. Or we could say find y double prime and take that and substitute it into this equation, right? Yeah, I think that's better. A little more organized. Okay, let's find y double prime then. So if y equals sine of x, y prime then is, and then y double prime would be, okay, so there's y double prime. I need to substitute it in here. So negative sine of x minus, what is y? Oh, they gave us that. Equals, and we're checking to see if it equals 0, right? Oh, what is that? Negative 2 sine x? Does that equal 0? 4 may be an x value, but does it satisfy for all x values? No. So then we can say y equals sine x is not a solution to y double prime minus y equals 0. Period. That's it, guys. How could they make this more complicated? They will give us this equation, then they'll have A, B, C, D, and they'll say which one is a solution. So you'll do the least amount of work if you pick the right one first. You know, you might have to check all 4. This might be what it is. Okay, here's the next one. Determine if this function y equals 4e to the negative x is a solution to that same differential equation. All right, we get y prime equals 4e to the negative x times negative 1, correct? Okay, that's where they're going to get us. We will forget the chain rule, correct? So then I can just take a second and write that. Negative 4e to negative x. You okay with that? And then y double prime, negative 4e to negative x times negative 1 again, because the derivative of e to the x is e to the x, and then times the derivative of the inside, 4e to the negative x. Okay, so there's the y double prime, 4e to the negative x minus y, 4e to the negative x. Is that equal to 0? Heck yeah. Therefore, y equals 4e to the negative x is a solution to y double prime minus y equals 0. How could they write this different? They might say f of x, and then say f double prime x minus f x equals 0, so on and so forth, right? They might say d squared y over dx squared, and they'll say y equals this, okay? We just got to be familiar with the notation. Questions on this one? Pretty easy? All right, see you new with this one. Okay, what's y prime, guys? C e to the x power. Constant times the derivative e to the x. That's the easiest one ever. Y double prime. Same? All right, so then c e to the x minus c e to the x equals 0. Does it equal 0? 0 equals 0. Therefore, y equals c e to the x is a solution to y double prime minus y equals 0. Questions on this at all? Pretty easy? Okay, so we have a process down. I could write any number of differential equations and just substitute, check, see if it works. Here's one for you. I gotta write this one out. Determine whether the function is a solution to the differential equation dy over dx equals 4y over x. Letter A. Let's try this one. Y equals 4x. Let's check to see if this differential equation is satisfied by the given equation. Well, what do we need? We need dy dx, we need y, and there's an x there. Okay, so what's dy dx? Okay, so we can substitute here. We're checking to see if it is equal. Back in the days when we were testing solutions like algebra 1 and stuff, I'd put a question mark over the equal sign because we're not saying it's equal. We're checking to see if it's equal. 4y. I have no idea what y is. I do? What is it? Oh, it's right here. I wish we had an equation that related y and x together. They gave it to us. So we have 4 times 4x over x. Let's see here. 4 equals, what would that be? 16. X over x. X is divided out. Does 4 equal 16? No way. I wish it did, right? Therefore, y equals 4x is not a solution to dy dx equals 4y over x. Okay, do this for me, please. Check to see if y equals x to the 4th is a solution to the given differential equation. It's crazy. All right, does this work? Okay, dy dx equals 4x cubed. We can substitute that in the left side. 4x cubed equals 4 times, okay, y is x to the 4th, and then we have x down here, and we're checking to see if it is true. Well, one of these cancels one of these. Oh, it is. Therefore, and then of course we could say y equals x to the 4th is a solution to the differential equation. Okay? Questions on that? Now let's find the general solution to this differential equation. Finding the general solution is finding the antiderivative. problem is we need to be a little more precise in our writing. Before, we just say, okay, what's the antiderivative of dy dx would just be y, correct? But here's the problem. If I take the antiderivative of both sides, right? Do you guys notice anything that's wrong with your knowledge of antiderivatives?
Yeah.
What do you mean? It's supposed to be a dx over here? Yeah, well, every time we've had an antiderivative, say like 3x squared, we've always had that dx with it, right? If we had an antiderivative of 3y, we'd have to have a dy with it, correct? So you'd have to have the same dy or dx, whatever, with the variable that you're trying to find the antiderivative of. We have two of them here, and none of them over here. How can we fix that? Well, we're dividing by dx in a sense, right? How can we undo this division by dx and move this dx over here? Multiply by dx, right? I don't think we've ever done that, have we? Maybe I might introduce it like really quickly a long time ago. This is called separating variables. We need to separate our variables. This is an important step on an FRQ on a AP exam. So we're going to multiply both sides by dx. So we'll have dy equals, now this is a whole quantity, this is the entire side we're multiplying by dx by, correct? So 4x cubed plus 1 dx. So first we need to separate our variables, and then we can take the antiderivative of both sides. We get a little more formal and proper with our separation of variables and finding the antiderivative or finding the general solution, because the problems are going to get a little more complicated. We're going to have x's and y's over here, and it's going to be a mess. Okay. Before we had fairly easy, convenient problems. This is set up appropriately now. We have one antiderivative with a dy, antiderivative with a dx, only x variables and a constant or two, whatever over here, and only y variables or nothing. We have a constant though. What's our constant on the left side here? Just a 1, right? Just 1. Okay, what's the antiderivative of 1 dy? Just y. Now find the antiderivative of this expression with respect to x. Okay, it'd be 4, and then I got x, add 1 to the power, divide by the new power, plus x, and then plus c. And I think we talked about a long time ago why we don't put a plus c over here, because it'd be a plus c and a plus c, and then they wouldn't really cancel out, but you'd have like a c sub 1 and a c sub 2, and if you add or subtract two constants, that's just another constant. So we just put the constant on the right side. That seems familiar. We talked about that before. Okay. Simplify this a little bit. Y equals x to the 4th plus x plus c. All right. Applying a little bit more precise writing to something we already know how to do. All right. They'd have to give us an initial condition. We could solve for c. Then we have the particular solution to this differential equation. How about this one? All right, if we need to find the general solution of this differential equation, we'll look at the setup, dy dx, and we have only x's on the right side. That's nice. That just means we need to multiply by dx on both sides and take the antiderivative. Okay, over here, that's going to be easy. That's just y. Right side. My goodness. What do you think, guys? We don't have an anti-product rule. You're going to take an x inside the radical? Good luck. Say again? That only work with sums or differences, I think. Yeah. A what? What would you be then? Yeah. So what would du be? Du be what, -1? And then bring your negative over, because we don't have a negative over here anywhere. Negative du equals dx. So this would be u, so we'd have square root u. We have a problem though. Solve for x, okay. So subtract, or I can add an x and subtract a u. X equals 5 minus u then. So our new antiderivative then would be antiderivative dy equals, okay, we would have 5 minus u. Oh, that's not minus u. 5 minus u, and then square root u, du, negative out in front. Taking care of everything. Now, since there's one item underneath the radical, now I think we can distribute, right? Okay, so that would be u to the half. So it would be 5u to the half power minus u to the first times u to the half, u to the 3 halves, parentheses around everything, and then du. Now I think we're set up so we can take the antiderivative both sides. Antiderivative dy, y plus c, but we put the plus c over here, equals negative, okay, u to the 3 halves times 2/3 times 5 minus u to the 5 halves times 2/5 plus c. Okay, rewrite. Y equals, so that'd be what, -10 thirds, and then let's substitute our u, 5 minus x, to the 3 halves, minus 2/5, 5 minus x, to the 5 halves, plus c. Oh, right here? You bet, thank you. Questions on this? All right, let's see what's next. We good? All right, let's see about this. Find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared at the point xy that they gave us. Just kind of over-explain themselves a little bit, as shown in the graph below. Keywords to pick out. Find the equation of the curve. So we need like y equals something, right? They gave us an initial point, an initial condition, a point that's on the curve, and has a slope of, slope, what does that mean? Derivative, that means dy dx, right? They're saying dy dx is y over x squared. So the slope of all the tangent lines along that curve is given by the function dy dx equals y over x squared. They gave us an initial condition, or a condition, right? We need to find the antiderivative, use this condition to find c, and there's our function, or our equation. Okay, start off with your differential equation. Now, we need to separate variables. That means collect all the y's and dy on one side, all the x's and dx's on the other side. Okay? So the only way I can get this dx to the other side is by multiplying, right? The only way I can get this y to the other side is dividing. So I'm going to have 1 over y dy equals 1 over x squared dx. Are we okay with that so far? All right, find the antiderivative of both sides. Okay, what's the antiderivative of 1 over y? Natural log, and then what? Okay, this would be, where are we going to put our plus c at? Right side. Because we have two antiderivatives, right? If we take the antiderivative of this side, it'd be like c sub 1. Antiderivative of this side, it'd be c sub 2. Combine two constants, what do you get? Another constant. So typically we just put the constant on the right side. Okay, antiderivative of x to the negative 2 power. Okay, it'd be x to the negative 1 times negative 1. So we're at this point. Okay. Solve for y. Okay, here's two things we can do right now. Number one, we could solve for c at this point right now. Okay. Number two, we could solve for y and then solve for c. It's up to you guys. What do you want to do?
Solve for y first. I just want to see how.
Who wants to solve for y first?
Yeah.
Who wants to solve for c first?
We do y after.
Oh my.
Yeah, it's 2 to 1.
Why do I even give you guys choices in the world? Okay, y is 3, x is 1. And you notice I'm not going to use my absolute value sign anymore? There you go. Okay, what did I say? X is 1. So what does c equal to? 1 plus natural log of 3. Okay, natural log absolute value y equals negative 1 over x plus 1 plus natural log of 3. Now what? We gotta solve for y. What do you do next, do you think? What are you talking about?
E.
What do you mean E?
Oh,
So you want me to write?
you do E to the negative 1 over x plus 1 plus ln 3 equals y.
Absolute value y?
Yeah.
That'll work. Simpler than this? What could we do? There's a number of things we could do.
You could get this square root, but you have to do the basis. Like,
What do you mean square root?
well, like, you take the root, like, instead of like the square root of 2, or you could do like the root, but the base of the root is negative 1 over x plus 1 plus 1.
How about this? Now we're going to talk about this a little more because we have a whole section on base e again. We could do e to negative 1 over x times e to the 1 times e to the natural log 3. Right? We could do that. How'd you get 3e? Where'd you get 3 from? Yeah.
Well, ln 3 is the power that makes e 3.
Oh, so that's just 3 then?
Yeah.
What's this?
Over.
Like that?
Yeah.
And we'll talk later a little bit more about how to get rid of that absolute value. But think about it, guys. Y is positive in our initial conditions. Do we really need the absolute value? Yeah. Okay, we'll talk more about this later. What time we got? Slope fields is a way to visually visualize solutions to differential equations of all possible graphs that you could draw. So slope fields are all possible graphs, or all possible representations of all the slopes. And if you kind of look at them cross-eyed a little bit, you can kind of see what the graph would look like. Not necessarily have to look at them like that. So in this particular situation, we have these slopes. Now, what does this represent? Well, it represents a piece of the slope, the tangent line. Okay, which represents the slope of the tangent line, right? It's not the entire thing, and it's at integer values, or I guess in this case we're at integer and a half values. Okay, what do you think the graph of the function looks like? Parabola. Now, y, so we could like draw our parabola in here. It's actually fairly decent. Nuts like that. Why do you think we could draw all these different ones? Because it represents all of them, right? All the possible graphs of that parabola, right? Exactly. So this is what your function would look like without knowing c. It's all these possible answers. And what does plus c do? That's just a vertical transformation, up or down, right? So we have to know an initial condition to draw the actual only one. And they would have to tell us. Okay, so you can tell just by the way these things look, it's kind of directing us towards that parabolic graph, right? Well, how about this one? I'll say it's a function. What do you mean? So you're saying it could look something like this? Like that?
Well,
or it could be like this?
Could it also be like x equals 1 over y or something?
Like this?
Because it has a horizontal asymptote of x equals 0. So it would be a function with respect to x instead of with respect to y.
Well, we'll say it's a regular function, and this would be the reflector. Could go up or down like this, right? It's not going to do both at the same time, okay? So it could be one of these various graphs. Now, typically what they ask us to do is draw one of these functions within an already made slope field, or they ask us to make our own slope field. This was a question on the AP test. Very similar to this right here. This is the derivative. That represents all possible slopes for that function, right? And we don't know the particular solution. They have to tell us. So what we have to do is sketch a slope field. We are going to make one of these for all the points given to us. Sketch a slope field of the differential equation on the coordinate plane below. Mr. Wally, how do we do this? No idea. Just kidding. But check this out, guys. What's this point right here?
1, 1.
So the point is 1, 1. That means x is 1, y is 1. That means the slope of the tangent line when x is 1 and y is 1 would be negative 1 over 2 times 1, which is negative half. That means the slope of the tangent line right here would be negative half. So what do we have to do? Just draw a little piece of that tangent line right here through the point 1, 1. What do you do then? We'll get to that. Okay, so negative 1 over 2. So it's going to look about like this. Correct? Pretty close. So down 1 over 2 or up 1 back 2. So it should go about like this. Just draw a little piece. Okay, how about the point 1, 2? 1, 2. So dy, dx. And you could say evaluated at 1, 2. Remember, we could do that notation. Okay, x is 1. Y is 2. Negative 1/4. So that'd be down 1 over 4. And what did you say? Less steep? Half as steep? You kind of have to imagine it going through this point and this point, right? Over here. Actually, farther over. My bad. That should even be less steep than that. All right. How about the point 1, 0? So dy, dx evaluated at 1, 0. X is 1. Y is 0. What type of tangent line would that look like? Vertical tangent line. Guess what? We don't draw vertical tangent lines. You just leave it blank because it's undefined, right? Every once in a while you might see one drawn, but typically we would not draw them. Okay? So what do you know about every time y is 0? So we don't have to draw any of these vertical tangent lines, right? Okay? All right. So let's pick some more values. How about 2, 1? dy, dx evaluated at 2, 1. Negative 1. So negative 1 right here. How about when x is 0 for all of these ones? These are all straight lines.
Oh, got it. Horizontal line.
Huh?
Horizontal line.
A horizontal line. So negative 0 over 2, that would be 0. So we'd have horizontal line here, horizontal tangent line here. What about 0, 0? Do not draw one because you have that vertical tangent also. It's undefined. Okay, so we have horizontal tangent here, horizontal tangent here. Apply them.